Hello and welcome to the presentation of the project 2019 called Implementing Task-Based Parallelism for Plasma Kinetic Code. Our project was developed in C++ where we integrated CUDA, OpenMPI, OpenMP, and StarPU for parallelization. In our project, we use plasma kinetic simulations that are performed for nuclear fusion reactors. The most widely used models are called particle-in-cell, which simulates the particles of the plasma, their fields, and many other features to obtain an accurate description of the plasma's properties. We mainly used a code called SymPic. For SymPic, we start with an initial distribution of position and velocities of particles. Then the particle mover updates velocities with electric fields, positions with velocities, and charge density with positions. After so, the field solver calculates the electric potential and electric field with the new charge density distribution. Then the results are saved into memory, and this is repeated for the next time step until the maximum time is reached.
This first version of SymPic that we've developed primarily utilizes OpenMP to increase performance. It was created to run entirely on CPUs to compare to other later versions which use heterogeneous GPU and CPU architectures. StarPU is used as a task scheduler even on this homogeneous system. Both OpenMPI and OpenMP were used to increase parallelization. The most computationally intensive section of code was the moveParticles function. The original algorithm for this function was updated and optimized for use with OpenMP. The new algorithm schematic is shown. It includes the initialization of temporary variables within the OpenMP loop and the creation of a new Boolean array for checking whether a particle is active or not. The OpenMP version is slower than the original version for less than a given number of particles. As the number of particles is increased, the observed speedup seems to level off at around twice as fast. This speedup is modest compared to the later other GPU versions.
We can now exploit further parallelism in our code using graphics processing units or GPUs. The particle mover accounts for up to 60 to 70% of the runtime of most particle-in-cell codes. Hence, we try to parallelize this first. You can see the CPU particle mover algorithm here. Note that the GPU has its own memory space. So before any computation can be done on it, memory has to be transferred to it. In our initial version, we copy all the required arrays to the GPU each time the particle mover is called. However, the runtime was greater than the CPU version. Hence, we decided to optimize this further. Note that the size of the particle arrays is much larger when compared to the size of the density and field arrays. Hence, we decided to create the particles in the GPU itself to eliminate these big memory transfers. Now only the smaller field and density arrays need to be transferred. We also did a few optimizations to enable vectorized processing in GPUs. We can now compare the code between the CPU version and the GPU CUDA version and see that there is some significant extra code. However, this gives us a huge performance boost. You can see here that the GPU particle mover is much faster when compared to the CPU version and gives us a speed up of around 5 to 10 times. We also visualize the computation and memory transfers using a visual profiler. This is our initial version, and you can see that the memory transfers account for much more time when compared to the computation. However, in our optimized version, you can see that the memory transfers are much negligible when compared to the computation.
After moving to GPU, the particle mover, we parallelize the field solver. First of all, in GPU, we allocate field arrays and copy some static values. We also have to initialize a CUDA library that performs basic algebraic operations in GPU. After so, the main loop is called, and we already have the particle data in GPU. So the field solver will obtain the solution for the electric potential by solving a tridiagonal matrix, and then we'll add the boundary effects and calculate the gradient in parallel for each grid point. We obtain the best performance for the particle mover in GPU and the field solver in CPU instead of the full GPU version. And this is for most of the cases. Also, the profiling indicates that this is because the GPU tridiagonal solver is slow due to the dependence of the calculations.
We can further improve performance of our code using heterogeneous computing. This means involving all available computing resources like multiple CPUs and GPUs. We have used StarPU to enable this. StarPU implements parallelism using tasks. Each task could be a CPU function, a CUDA kernel, or an OpenCL kernel. The main advantage of StarPU is that the same code can be run on multiple architectures without much change in performance. We can see here that there is some extra code required to initialize a task and launch them. We also did some experiments like enabling asynchronous data transfers, partitioning data and launching multiple tasks, and we studied the performance in each case. We also visualized the StarPU particle mover task using a visual profiler again. Note that here these data transfers are done without any explicit code written for it. Hence, the memory is managed here by the StarPU scheduler by itself. Finally, we would like to thank our project head Professor Leon Kos, our project mentor Ivona Vasileska, as well as Leon Bogdanovich and Pavel Tomzic, all from the University of Ljubljana, for all their help, guidance, and access to the amazing computing facilities in the Lecker laboratory.